think I'll just start. If anyone walks in, that's there. Good morning. I'm Philip Paeps. By daylight, I work on embedded and real-time systems, and at night I am a FreeBSD hacker. At the moment, I spend most of my time as the core team secretary, herding the core team. But when I'm not doing that, I like to play around in the kernel. And I'm going to talk to you about the crypto acceleration framework we've got on FreeBSD. It's actually not just a acceleration framework, but it's a crypto generalization framework which happens to also accelerate cryptography if hardware is available. And as we shall see, it can also decelerate cryptography if hardware is available, but the processor is faster. I got involved with the crypto accelerator when I was playing with my Geode CPU, and I saw a cryptography processor on board, and I thought, hey, it would be fun to play with this. And I found some patches to support this thing, which I then committed to FreeBSD, and it turned out they worked well. And by the usual principle of you touch it, you own it, which prevails in the FreeBSD community, I've not been allowed to let go of this thing. People come up to me at conferences and say, I have this patch, or I have this problem with the crypto layer. So I thought I'd explain a bit how it works. First I'll put the cryptography layer in some context and say why we need this thing. And then I'll discuss a bit about how the framework works and what I want to do with it. And finally, I've got some performance measurements I took a while back. There's a bug on one of my slides, but no one noticed the last time. And I'll share those with you. So, a bit of context in Userspace. Surprisingly, things are much easier than in the kernel. Usually, applications will link with a library like Openssl, which is in the base system, or VPN, which is in the ports, to do their cryptography for them. And this is a widely accepted interface, which is well known. And few applications will actually reinvent wheels to do cryptography. In the kernel, however, we've got a number of subsystems using cryptography, the main one being IPSEC, which is very performance critical. And we've also got some block devices like GBDE and Jelly, and recently we've also got ZFS. All these things want cryptography, and up to rather recently they were all reinventing their own cryptography, which led to a lot of code duplication and other problems which we didn't really want. So what we actually wanted was something like Openssl, but in the kernel. For various reasons, it would not be a good idea to put Openssl in the kernel. One of the main ones is that it's an enormous block of code which mainly wants to do SSL and accidentally also does crypto bits. So the opencrypto framework was found. It was originally developed for OpenBSD by Angelos Keromitis, probably pronounced his name slightly differently. And he provided a consistent interface for Userspace, and I'm supposed to speak slower again. He developed a consistent interface for software and hardware cryptography in the kernel, which was fairly extendable and modular. So Sam Leffler in 2002 found this crypto layer and tried to port it to FreeBSD. And he discovered that the OpenBSD kernel is somewhat different from FreeBSD, particularly with respect to multiple processors and other performance aspects. So Sam Leffler wanted to use the opencrypto framework to accelerate IPSEC if hardware was available, and basically found himself rewriting the code from OpenBSD. Very little of the original code from OpenBSD now remains. I will go through some of the bits that are still there. And most of it has been rewritten for FreeBSD. There is still pseudo-compatibility with the OpenBSD interface, but I would like that to go away because it's stopping us from making progress. So the current state is that other than the copyrights, some parts of the software crypto, it's mainly FreeBSD codes, and it's actually fairly performant. As I mentioned, the opencrypto framework wants to be Openssl, but inside the kernel. So one of the requirements is that it should reduce code duplication instead of every kernel subsystem inventing its own way to take a hash or or encrypt something. They should use the opencrypto header, which is crypto defaults called H, and they can use a consistent interface to take care of all their encryption needs. The opencrypto framework automatically takes advantage of hardware if hardware is available. I'll explain how the hardware works in a little bit. And if no hardware is available, it will use a software crypto module, which is actually the bit that's like Openssl is the software crypto module. It implements all the different crypto algorithms. The crypto framework has two modes of operation, which is a bit like Openssl also has two modes of operation. It can do SSL or it can do just crypto. But in the opencrypto framework, we've got a session-based mode where a crypto consumer says, I would like to use the following algorithm and with the following settings. It provides a key, it provides initialization vectors, and it sets up a number of descriptors where it will find its data and where it would like its data to be written. And the sessions are cached per driver, which is, well, it has advantages and disadvantages. One of the advantages is that the information can be cached in hardware. So if you've got hardware which knows about states, you can program the hardware once and recycle the hardware programming for every single operation. Another nice advantage of the session-based mode is that you can set up the session to do multiple operations in one, or multiple transformation in one operation. So if you want your data to be encrypted and then hashed, you set up an encryption operation and a hashing operation, and you send the transaction to the kernel, well, to the framework actually, because you're inside the kernel, and both operations will be done. There is also a sessionless mode, which might seem simpler, but it's not. It's used mainly for generating keys and for offloading mathematical transformations. Some cryptographic hardware has silicon which can do modular experimentation or similar operations, which are faster to do in hardware than in software sometimes. And the sessionless mode takes advantage of this. You tell the framework, I have some data here, I have two pieces of it, and I would like to turn it into one piece of output data, and I would like that data to be written here. You dispatch the transaction to the hardware, and you will get a message when your operation completes. This sessionless mode has no support for multiple operations, because generally hardware tends to support only one mathematical operation to be performed like that. Both of these methods of operation are asynchronous, which is unlike OpenBSD, where I believe they're still synchronous. The reason for this is that consumers of the crypto framework are not necessarily processes, so drivers can't sleep on operations. As the consumers are in the kernel and likely to be kernel threads, you can't sleep. So what happens is you register different callbacks with the framework to be called when your process has been completed, and then you will be woken up because you will still be awake, but you will be signaled that your operation is complete, and all your status information and possible errors will come back through a callback. And there's a special callback to tell you that there were no resources available and you should try another session instead. So how does this thing work? I drew a little picture of it. These pictures say 1,000 words, so I can only speak very slowly here. Inside the kernel, we won't bother much with Userspace, which I like to call trouble. We have the opencrypto framework, which has the different drivers registered with it. CryptoSoft is the software crypto driver, which I will explain in excruciating detail shortly. GLXSB is the one that got me into trouble in the first place. It's a driver for the geode crypto block found in AMD geode processors. Hyphen is a rather oldish crypto processor, which is still quite popular. The Userspace VPN boards use them. And UBSEC is a blue steel one, which is bought by Broadcom, and I believe they killed the product line, but it was actually a fairly good processor. And at the moment, I think we have about 7 or 8 different hardware crypto drivers, and I would actually like some more. So on the bottom side of the framework, the drivers register and tell the kernel that they will be providing these operations with these constraints. And inside the kernel, the opencrypto cryptodev header provides a consistent interface to the drivers for kernel consumers. At the moment, IPSEC and Jelly are the main consumers of this. Jelly is the Geom encryption layer, and IPSEC is obviously IPSEC. The advantage of having them sit on top of this is that if there is hardware available, they will use it automatically, because the crypto framework will automatically dispatch operations to the hardware. If no hardware is available, the crypto softs will provide the cryptography. So if no hardware is available, the framework provides an abstraction so that these guys don't need to re-implement the wheel every time. For Userspace, there's the dev crypto interface, which exposes all the functionality which the kernel can get from cryptodev to Userspace, and that's mainly used by engines of OpenSSL, as I shall show you, but it doesn't have to be OpenSSL. Others can easily use it too. So the driver side API, which is what these people implement, is fairly simple. The drivers tell the OpenCrypto framework, I support framework A, algorithm A, algorithm B, algorithm C, and I know about key sizes of 128 bits, 256 bits, whatever. And they give the framework callbacks, which are called when sessions need to be created or destroyed. And one of the drawbacks is that the sessions need to be managed by the drivers, which is a bit of a problem because it's not possible for sessions to migrate from driver to driver. So if you've got a driver in a PC card, you eject the PC cards, your session will, well, still be there, and if you try to use it, things go boom, which is not really what you want to have. There is supposedly in the code provisions for migration, but nobody implements them, which is one of the things I would have changed. Another problem with the driver-side API at the moment is that there's no real prioritization support. So if you've got 6 different crypto cards sitting in your computer, 1 really fast one and 5 really slow ones, the 5 really slow ones will be used with exactly the same priority as the 1 really fast one, and your crypto acceleration becomes crypto deceleration, which is not very helpful. The interface, as I said, is mostly compatible with OpenBSD at the moment, which I want to go away. I'll actually show an example in the code where this is a problem. This is the this is the GLXSB driver for the geode crypto block. In its crypto register function, which is still completely compatible with OpenBSD, there's these 2 function pointer arguments at the back. In FreeBSD, we have got newBus, where we register device methods in an object-oriented way. OpenBSD does not have, or did not have, when that was ported, this particular method. So drivers had to pass pointers to their session management functions in the crypto register function. And here there are null pointers, because we have, as I said, the dev methods. Oops. There we go. Type. We have the dev methods here at the bottom. We've got a callback for new session, free session, and process. So I found that if you fill in the function pointers, very bad things will happen. So that will need to go away soonish. So So mostly compatible with OpenBSD is a myth. It's fairly easy to port crypto drivers from OpenBSD, but it's not a one-to-one job, so I think it's probably best if we break the compatibility at one point. So, going back to the architecture, the software crypto device, which is this guy, is exactly like a hardware device, only it's implemented in software rather than bits of silicon. It's implemented as a generic transformation system, so it's not actually limited to cryptography in any way. If you wanted to do matrix transformations for whatever reason inside the crypto API, you could do this. This code is the only thing that's still left from OpenBSD, which is virtually unchanged. It supports most relevant crypto transformations like MD5 and SHA-1 and all the other usual ones. And it's fairly flexible and easy to implement. If you have no hardware available, you will fall back to this feedbacking again. The hardware accelerator, as I explained, has support for a number of different hardwares now. We've got the Geo crypto block, the hyphen cards. Padlock is quite popular. It's found in all these cheap VIA embedded processors. SafeNet, I have no idea what it is, but it's reported to work, and if I break it, I get complaints. And UBSEC is the fast Broadcom Blue Steel one. Going back to the diagram here, the Userspace Interface is what DevCrypto is doing. There we go. The Userspace Interface is like the kernel interface. It's asynchronous. Generally, you just need to do ioctl to create a session, do ioctl to destroy a session, set up your transactions, and it will just work. Currently, the only consumer of this Userspace Interface is Openssl, which has an engine called the CryptoDev engine, which is not enabled by default in FreeBSD because it has some serious performance drawbacks if you enable it and you don't have hardware acceleration, or if your hardware acceleration is slower than your CPU. I'll show you the performance numbers in a bit, which illustrate this quite clearly. And that should say not on by default, because this is as I explained, the framework has a number of issues, and I'd like to fix these. Some of the issues in the kernel are that sessions are managed by the device drivers, which is something I would like to get rid of first. I would like to add a session management layer so that it would be easy to migrate sessions from one device to another device, or to load balance sessions over different devices. That's the prioritization support I already explained as well is not very good. And if you have a fast device and a slow device, preference should be given to the fast device rather than the slow device. Another problem which I have not explained yet is that there's very limited flow control opportunities. These mainly show up when you're doing IPSEC. As long as you're doing very large packets, IPSEC will work pretty well. But as soon as you have hundreds and hundreds of thousands of small packets going into the crypto layer, it slows down quite a lot because you're basically hammering the bus and not so much the CPU, and the bus is going to be your limiting factor. I have a number of ideas for fixing this. Rafael, was that a question?
No.
Oh, you were just
no.
You were just confirming that this is a problem.
Yeah. We have seen exactly these issues with a great number of small packets.
Yeah, and also as there is no way to migrate sessions, if you've got 5 cards, you will basically always be hammering the same card because the sessions are per device. So if it was possible to have your session per driver or per set of cards, that would probably fix things in a very elegant way. Besides the kernel issues, there's even more problems in Userspace. Userspace is generally more of a problem than the kernel, but that's my bias. The main problem is that Openssl engines are an all or nothing interface, which is the main reason why we don't switch them on by default in FreeBSD. If Openssl finds an engine is available to take care of your crypto operations, it will use it. So in the case of the opencrypto framework, there will always be hardware available, even if there is no hardware, because the crypto soft behaves exactly like a hardware device. And you might say, why is this a problem? The crypto soft is a fairly performance device, but the problem is if you're going to be context switching continuously between user space and the kernel, especially if you're doing crypto operations on large blocks of data, you're going to be spending a lot of time copying in and out of the kernel. On Intel, this is generally fairly efficient, also because the kernel memory manager has some few tricks to make this fast. But some other architectures like MIPS, or ARM especially, if you context switch, you have a complete TLB flush to waste your time for you. So you're going to maybe do the operation in the kernel in a matter of microseconds, but your context switch will take you milliseconds, which you don't want to do. And the OpenSSL implementation of the crypto algorithms tends to be at least as fast, and sometimes even faster than the kernel implementation. So context switching, you really don't want to do. As I'll show in numbers, if you do enable the OpenSSL engine on a fast machine, you're actually going to get crypto deceleration rather than acceleration. You can do it 10 times as fast or 100 times as fast, staying in user space than in the kernel. One of the ways I would like to fix this is by adding a heuristic, where I would send the first 10 or 100 crypto operations down to the crypto layer, and then I would tell OpenSSL one way or another, please back off, it doesn't make sense to use this, you can do it faster yourself in user space. So yes, the future directions, this is where we want to go, and I would actually like some feedback from people who have time to work on this with me. The first thing I want to implement is a session management layer. I've got some ideas about this, but the main idea I want to implement is load balancing across different drivers. A number of embedded CPUs have got crypto blocks in silicon, which are good as long as you have fixed size keys and your operations are a fixed number of bytes. But if you've got anything different, it's going to be slower. So then I would like to say use the software crypto, it's going to be faster. And I'd like to do the load balancing. So if I've got five hyphen cards plugged into PCI slots or whatever, well, that's not very likely. I would like to use each of them in turn and keep them all busy rather than hammering one of them and having the others basically gather dust. And the last part, telling user space that no hardware is available in your software, will probably require some changes to OpenSSL, because OpenSSL has no way to say that the engine is not actually sensible. Another change I would like to make, which I think Rafael is very interested in, is improving parallelism. The hardware is now, the original crypto hardware tended to be basically one piece of silicon which could do one thing really quickly. Like, I can do AES with 128-bit keys really quickly, but if you give me AES with 256-bit keys, I'm going to be really slow about it because I'm going to cut these into two operations. Newer hardware is evolving towards multiple execution blocks, where you would have an execution box which can do AES with one size key, another one which can do AES with another size key. And our crypto framework has no way of addressing this. Rafael described the device to me, which can actually do multiple algorithms as well?
Yes, it can do basically separate engines for hashes, for encryption.
Yeah, so now the way we would have to address this is by writing 4 different drivers for the same device, which is not going to work because it's one device. It's not going to work well. Plus the drawback that you can't load balance across the multiple devices. I would also like to provide a method for flow control, where somehow the crypto framework could tell its consumers, oh, stop, you're sending me too much data too quickly. Please use another driver for the time being, or please slow down a bit, or few operations. Now, if you're going to try to send data really quickly, you're basically going to be waiting for things to and I've also, this is an idea I've had very recently, I'd like to pin the sessions to a single CPU because the system is asynchronous. What can happen is that you can wake up on a different CPU than the one where you started your transactions. So both, you're going to be copying your data in, and then you're going to be copying it out, and you're not going to take advantage of caches, which is going to slow things down. On embedded systems, this is probably not going to be much of a problem, but if you are using crypto acceleration to speed up SSL on a busy web server, you don't want to miss caches too much. That's going to hurt. Another painful item on my to-do list is more hardware supports. Currently, all the drivers we have got in the tree are for low-end embedded hardware, where it makes sense to accelerate crypto. I've seen manufacturers sell really high-end crypto things, claiming speeds of 1.5 gigabits per second IPSEC. I would love to borrow this hardware and implement support for it and make it faster. And, well, if they don't need the hardware back, I'd love to keep it as well. But it's writing device drivers is a small matter of programming. For instance, the GLXSD one is it's less than 1,000 lines of code to implement a device driver. So if given access to the hardware, it's usually a small matter of programming to make it actually work. So I promised you some numbers of crypto acceleration and deceleration. The simple test is Openssl speed. If you run this on a Socrates, which is a 500 megahertz geode platform, and it has an accelerator for AES with a fixed size 128-bit key. If you do the speed test on the CPU rather than the crypto block, you're going to be going fairly slow, and depending on your data size, the speed is not going to change much. If you, on the other hand, enable the cryptodef engine, which would be used if it was on by default, you're going to get, for key sizes which are not supported, you're not going to have much change. Key sizes which are supported, you're going to be much faster, much faster, and much faster again. So as long as you use the native key size, it's going to be really fast. A more reasonable.
What were the packet sizes? The key was always 120.
Yes, the data sizes, sorry, not the key sizes. Yeah, you pass the data down in a more useful test is encrypting a large file. Not very large by some people's standards, but I thought 350 was a nice number. If you don't use the engine, it's going to take you a minute of real time, which is, well, slow. Whereas if you enable the cryptodef engine, you've done it in 18 seconds, which is three times as fast, at least. This is on an embedded device with a slow CPU. If we look at the other side of the equation, where we've got a fast AMD64 machine, this is a machine which has a 3 gigahertz AMD64 processor, and it's got a really slow hyphen card sitting in a 32-bit PCI bus. You are going in hardware, on the CPU, and things are going fairly fast. But as soon as you enable the crypto accelerator, you slow down dramatically, and at 8K of data, you're basically halving. At 16 in really small packet sizes, your speed is basically divided by 10, which is not a good idea. If we look at encrypting a large file, which is a much nicer test, the CPU can do the encryption and decryption in less than 10 seconds, which is very fast. But as soon as you enable the engine, the time it takes doubles, which is not optimal. So if Openssl could be taught that the hardware made no sense, then that would be a good idea. And that concludes my slides, which means that I have been speaking too fast for this audience. So any questions or comments, or people who have too much time and would like to work on some of these, perhaps as a Summer of Code project? I see our Summer of Code ideas man is sitting in the front row.
What processes, what accelerators do you have in mind to support?
There's one, Cavium makes the Nitrox crypto processors, which accelerate IPSEC, but I've never seen one of these devices live.
They usually connect to PCI or mini PCI?
Some of them even do PCI Express.
Oh, okay. Yeah, that's actually better.
And the Nitrox ones, I think they may be offloading IPSEC completely, but the data sheets on the website are the usual marketing data sheets. We go this fast, but they don't tell you how they do it.
Yeah.
So,
Cavium also has built-in crypto support in their MIPS processors.
which is probably the same silicon from there. No?
Oh, it's a very different interface. The MIPS processor, they implemented as a coprocessor, so if you, just like you would have an add instruction or a floating point instruction, you have load all these registers and do the steps of the first step of the Diffie-Hellman.
Yeah.
So
that's also not supported by the crypto layer, but it shouldn't be too difficult to do. The crypto layer rather assumes that you're going to be a PCI device or something. It doesn't take into account things which have special instructions. It shouldn't be too difficult to teach it about it, I think. But I think the first step will be adding support for these PCI Express things. But in some cases, I think they might be offloading the entire IPSEC, which is probably going to be another challenge to do, because offloading crypto is fairly easy. You just tell the hardware, here are some bytes, please give me some other bytes, which look a bit more random. Whereas if you want to accelerate IPSEC, you're probably going to need to do session management and implement ICE on top of that, which is going to be more challenging. Does anyone have any hardware for me to borrow back? Yes.
I'm Masanobu Saito from Internet Initiative Japan. We are providing Internet expert. We are developing many IPSEC VPN routers.
Okay.
I show you main products for basement for
Good.
And one question. You talked about load balancing, and if we use many IPSEC processors with different devices for them on different performance,
Yes.
and if you encrypt or make packet into them, and if the performance is different, or packet may be, the order of the packets will be changed.
Yes.
Do you think is it a big problem or a trigger problem?
I think, if I understand the question correctly, you have problems with packets not being ordered.
Yeah.
I think, yes, that's going to be a problem, because the crypto engine will want to do the operations in order. You will need to serialize them, so that's not going to be good. If we introduce more parallelism in the layer, then you could do your operations out of order. You could send one packet to one crypto accelerator, have it done, wait for it to complete, send another packet down to another one, wait for it to complete, and then when they are all done, you just pass them on to wherever they're needed. At the moment, I don't think that's possible, because you're going to have to serialize, because you're hammering one device. But I would like to fix that particular problem, and if you've got some hardware for me to play with, I would love to. Does that answer your question? Or? Else? Yes?
Can you return to the slide with testing of slow CPU, fast CPU and slow engine?
Fast CPU and slow engine. This one. Fast CPU, slow engine.
Yes, but the next one with time output.
Yes. Time outputs.
Well, I see in the second case the real time is larger,
Yes.
but the CPU loaded time is smaller.
Well, yes, of course. In the first case, you are actually using the CPU, whereas in the second case, you are offloading the crypto to your crypto hardware.
I think on the busy system, which does not only encrypting, but another tasks.
Yes, yes, of course. That's it's always going to be.
It can be good.
Yeah, well, it's going to be a trade-off. If you've got a 3 gigahertz CPU running things like a busy web server, you're mainly going to have I/O loads to do the web serving. The CPU will not be doing very many interesting things. So if you've got hundreds of crypto operations and hundreds of sessions waiting for encrypted data, if you could do them faster on the CPU than in the hardware, then it's probably better to do it in the CPU. But yeah, I agree it's a trade-off. If your CPU is better used for other operations, then you probably do want the hardware offloading, even if it's going to be a bit slower. But again, I think there should be a way to tell the crypto layer that this is your particular use case. So there should be some tunable that says, I am interested in keeping my CPU busy, or I am interested in cryptography as fast as possible. Which, yeah, but yes, I agree. The CPU in the second case is twice as busy. Twice as 7 times. I should look at my own slides.
I'm wondering if the hardware has encryption hardware. Previously, you will use hardware power automatically.
Yes.
By the way, we can turn off the hardware feature by syscontrol, something like that.
You could just unload the device driver.
Ah, yeah.
If you if there's no device driver for the hardware, it's not going to be used. If it is, I would be.
Yeah, which isn't very convenient. Right?
It's not very convenient because we don't have any session migration support. If for some reason there's a crypto consumer which creates the session that never frees it, you can never unload the device driver. As I mentioned, the sessions are maintained by the device drivers.
Yeah.
So if you set up a very large session with, say, 20 different operations on very large data, you're going to have this huge session sitting, consuming kernel memory, which is not very optimal. So I would like to find a way to, well, at the moment there is a way to unload. I've implemented it in a couple of drivers. Wait for the sessions to shut down. If they are not shutting down,
you can drain,
just destroy.
You can drain the system.
Yes, drain. But what I've done for GLXSB is basically wait for a while, and if it's not going to go away, just shoot it.
Thank you, I understand.
Question. So you're talking about very small packets have a high per packet overhead.
Yes.
And so that causes a big problem.
Yes.
Is there some way you could maybe batch those and take a bunch of small packets and just put them in one transaction instead of lots of little transactions? And trade some latency for some throughput?
Yes. That would fit in well with the session management layer I mentioned somewhere. Yeah. Well, actually, it wouldn't fit in. Just create a session and say this session, before it can start a transaction, needs X amount of data.
Right.
And then just batch them up, send it down.
Or if you're waiting X amount of time and then more data doesn't come, then you say, okay, fine.
Yeah, just do it. Yeah. But the problem will also be because it's asynchronous. Somehow you'll need to tell all these guys upstairs waiting for you, and now you are done, and now you are done, and now you are done. So your latency will probably
possibly be in the right order too.
Well, not necessarily. You can wake up your consumers in a different order. Hopefully, they will do the right thing. But you'll need to wake up all these guys at some point. So you'll probably be increasing latency at an unacceptable sort of rate. So I don't think batching is going to be a good solution. I think load balancing is going to be more the way you want to go. Instead of batching up operations and sending them down to the hardware, maybe at a slower rate, just add more hardware or use the hardware more effectively. Yes.
But if you have hundreds of thousands of little packets, then
yes,
people aren't waiting that long for you to batch them.
True.
Because there's always more coming.
There's always more to cover.
Yeah.
And then in that case, it probably makes more sense to keep the CPU busy than keeping the small piece of silicon sitting off a 32-bit PCI bus. Very busy.
Yeah, I have a question exactly on this slide. The load balancing and the heuristics could maybe be folded together. Do you see it that way? Because
yes.
Your heuristics, you're trying to find out which is fastest.
Yes.
It might be the software which is fastest. Or is your heuristics going to go that far and tell your consumer, I am actually bad in every case, do it yourself?
Yes, I would. Yes, that's precisely what I want to tell Openssl.
Okay, so that's the last step.
Yes, there's no order in this. I just need them all to be done.
And actually, that's my other comment. I'm being a bit loud here, but the opencrypto right now is abstracting crypto devices. And
yes.
actually what you want is to abstract crypto sessions.
Well, it actually abstracts crypto sessions, but,
yeah,
in a bad way.
But they're sticky and
they're sticky. Yeah,
you want to actually have not sticky.
I want to have a session. Well, the current layer is very good at dispatching to hardware and abstracting crypto for kernel consumers, but I want it to be better at also managing sessions. So I think if we just stick a session management layer on top of what we've got now,
yes,
things would be.
The consumers would be hitting the session layer.
Yes, and the session layer should. So actually, the opencrypto framework just needs to get smarter.
Mm-hmm.
At the moment, the opencrypto layer is 4 callback functions and lots of memory. Whereas it should be, it should be more intelligent before hitting the hardware. It should queue things up and do things cleverly. So I think there's a good summer of code project in here. I should write it up. Anyone else?
You also talked about one other optimization technique of using polling mode.
Yes, yeah, I can actually show that. I've done that in this driver. If I can find it. Yes. I found, Patrick, who wrote this driver, and we found that if we're going to wait for an interrupt for the operation to complete, it's actually going to be slower than if we just busy wait. So we spent some time looking at how long does the hardware take for different transactions, and we sit there and poll. Rafal and I discussed during the Dev Summit a couple of days ago that we should extend the kernel polling framework, which is currently only used by network devices, to also be able to poll crypto devices. And I don't think, unless anyone wants to contradict me, I don't think there's a reason why we shouldn't do that. The polling framework should be device agnostic. So yeah, this busy loop this ties in with what you said as well. Your CPU time will increase because you're busy looping here, but your real time will go down. So for this sort of construction, there should be some kind of sysctl or some other tunable which says I would like my CPU to be busy, or I would like this to go as fast as possible. Anyone else? Thank you for listening.